All right, let's talk about short exact sequences. So, definition. If we have two group homomorphisms, phi will be a homomorphism from G1 to G2, and psi will be a homomorphism but from G2 to G3. Man, is my marker already starting to run out a little bit? So if this and this, then this diagram, G1 to G2 to G3, so these are like a sequence of functions. So if we consider the group G1, and then we have phi which maps G1 to G2, and then we have psi which maps G2 to G3. This is exact at G2 if the kernel of psi is equal to the image of phi. And let's see here. So then, what's going to happen if we look at psi composed with phi? Psi composed with phi of G, if you take an element of G1, phi is going to send it to something in the image of phi, but the image of phi is the kernel of psi. And so since it's in the kernel, since it's in the image of phi, it's also in the kernel of psi, and psi will send anything in its kernel to the identity. So this is going to be I'm going to call it E3. I don't like that notation, but I'm going to use it anyways. I'm going to put it on the bottom just so that it goes in the same place where the G goes, or the 3 and the G goes. So then this equals this for all G and G1. Okay? Let's see here. So if G1 is just the trivial group consisting of just the identity element, so let's actually write that as E. Then, let's see here. Exactness at G2 occurs. I don't think that's how you typically call it. You don't say exactness at G2 occurs. You say like the sequence is exact at G2. But I figure this will allow me to write less, and I also get to use the word exactness, which actually is not a word. But now it is because I used it. This occurs if and only if. So let's see here. What can that tell us about phi? So this is a homomorphism. So the image of phi is just going to be the set consisting of whatever phi sends the identity element E to. But this is a homomorphism, so it must go to the identity of G2. And so the identity of the G2 is the image of phi, but that's also the kernel of psi. So the kernel of psi is just the identity element. So this is if G1 is just the identity, then we're exact at G2 if and only if psi has kernel equal to just the identity element, which means that psi is injective. And of course, going in the other direction if psi is injective, then the image here is E, and so, yeah, that's obvious. What about if G3 equals just the identity? Then, what do we have? Then exactness at G2 occurs if and only if. So let's see here. The kernel here is everything that maps to the identity. But everything will map to the identity because G3 is just the identity element. And so the kernel is all of G2. But the kernel of psi is the image of phi. So the image of phi is all of G2, which means that phi is surjective. So that's kind of nice. We have this relation between letting this be 1 and letting this be 1, and then what that tells us about the relation between exactness at G2 and the homomorphisms phi and psi. So let's see here. So we have this corollary to the fundamental theorem of group homomorphisms, which we did last time. So if phi from G to G prime is surjective, then phi prime is, that's not right. Should be G prime. G prime is isomorphic to G mod the kernel of phi. And that's just a straightforward application of the or straightforward conclusion from the fundamental theorem of group homomorphisms. You can just go back and check that. Or let's see here. So then equivalently, if we consider E, you know what, instead of E, I'm just going to use 1, because that's how we usually write these short exact sequences, is 1 going to the kernel of phi, going to G, going to G prime, going to 1, is a short exact sequence. Which means that the above is exact at the 3 places in the middle, the places where it could possibly be exact. So the kernel of phi, G, and G prime. So of course, what are these maps going to be? This map, there's only one thing. We're just going to send the identity to the identity. And that's all that happens. This map from the kernel of phi to G, this is going to be given by inclusion, because the kernel of phi is a subgroup of G. If we go from G to G prime, that's just our map, our homomorphism phi. And then of course, g prime going to 1, that's just going to send everything to the identity element. So let's see here. You can go ahead and prove that this is equivalent to phi being surjective and just thus giving us this isomorphism. But let's actually just make sure this, let's do a sanity check. So let's kind of look at everything that we've said so far. So exactness at kernel of phi. We know when G1 is E, then exactness here occurs if and only if that map is injective. So the inclusion map needs to be injective. Well, the inclusion map is injective because it maps everything to itself, and it will not map two different things to the same thing because two different things aren't the same themselves. So that's why that holds. And then similarly over here, so we have 1 over here at this side, so that's like G3 being 1, and that happens when phi is, where did I write it? Phi is surjective. And of course, phi is surjective because that's one of the things that we're saying here. And so we have the short exact sequence. And then the kernel of I being the image of I being the kernel of phi. Well, the kernel of phi, obviously the inclusion map is going to map the kernel of phi to the kernel of phi. And the kernel of phi is the kernel of phi. And so we definitely have exactness at G. And so this turns out to be, so that proves that if phi here is surjective, then this is a short exact sequence. And then you can prove, well, yeah, it's kind of easy to see that the other way it also holds that if this is short exact, then this must be a surjective map because it does the things that it do. So that's that. So let's do some more examples of short exact sequences, and I have to come over here and open up a new roll of paper towels because I did not plan well. Oh hey, actually look at that. I do not have to open up a new roll of paper towels. All right, let's look at an example. Let's take, we go from 0 to Z to Z to Z mod 5Z to 0. So this is phi. With phi n equals 5n is a short exact sequence. I got it all. Okay, so why is this a short exact sequence? Okay, well, I guess I wrote 0 here because this is addition and the identity in addition is 0. Obviously this map is going to be the thing that it is. This map's going to be the thing that it is. So we need this to be injective. We need phi to be injective. Psi is just going to be in the inclusion map. We need psi to be surjective, and we need the image of phi to be the kernel of psi. So let's see here. Phi, we need to be... Phi we need to be injective. No. Wait, what? Oh man, if only I hadn't erased the definition. Oh, I have it right here. Okay, so what do we need? We need, so because we've got the 0 on this side, so when G equals 1, we need this to be injective. So phi of n is going to be 5n. Is that injective? Oh, yeah, of course. We're just multiplying it by 5. So this is going to be all elements of the z, this is going to be all multiples of 5. And so if you have two different elements of z, then, so if a is not equal to b, so if m is not equal to n, then 5m is not equal to 5n. Because if they were equal, then you could just cancel it and you'd have m equals n. Okay, so phi is injective. Is psi surjective? Right, what we're doing is we're just modding out here by 5z. And so, obviously that's going to be injective. And because we're modding out by 5... Right, so 5z, so z is an abelian group. So this is actually not that interesting of an example. So z is an abelian group, so 5z is a normal subgroup, and so modding out by it gives us a group. And this map, taking this natural homomorphism, taking z to z mod 5z is going to be surjective, because it's going to hit every single coset here. And of course, we know that the kernel of this map is going to be exactly all of 5z. But 5z was the image of phi, and so the image of phi is the kernel of psi. And so this is the short exact sequence. How about another example? We're going to go... let's remember how determinants work. Let's just take GL2C, and we're going to map to C, C cross, which is just C without 0. This is a homomorphism because, now first of all, yeah, so this is GL2C, so anything in GL2C is going to have non-zero determinant, and so that's why we had to exclude, well, we didn't have to exclude 0, but it makes it nice. Also, this is C with multiplication here, and so that makes this a group. It would still be a group if we had 0 in there, but anyways, this will be nicer. But why is this a homomorphism? It's a homomorphism because the determinant of A times B equals the determinant of A times the determinant of B. And here this is matrix multiplication in GL2C, and here this is multiplication in C cross. Okay. So now here, determinant is surjective, because given any complex number, you can just imagine the identity times that complex number. And that will be an element of GL2C because that complex number is not 0, and we're excluding 0 here, and so the image is surjective. And then its kernel is going to be the collection of things. Remember, this is multiplication, so the identity is 1, and so the kernel is going to be the things which have determinant 1, and so this is SL2C. Which is just the elements of GL2C which have determinant 1. Thus, we have 1 going to SL2C, going to GL2C, going to CX, going to 1. Thus, this is a short exact sequence, the following. Because, let's see here, we discussed that, so what maps are we having here? This is going to be inclusion, this is going to be the determinant. So the inclusion is obviously going to be injected. So this is 1, This is one. Inclusion is obviously going to be injective. The determinant we just said was surjective, and the kernel of the determinant is SL2C, which is precisely the image of SL2C under the inclusion map. And so there we go. And then let's see here. There's only one more example in this section, but it has to deal with permutations and like the sign of a permutation, and that's actually something that we'll discuss later in the lectures. So instead of discussing that now, I'd rather leave that until later, because I'm just going to bring up a whole bunch of stuff that relies on a whole bunch of things that I haven't proven yet. But hopefully these examples should provide you with enough, I don't know, should sort of get you a feeling for what short exact sequences are like.